Okay, so hello everybody again. So today we're going to do some very brief summary of section 2 that we essentially finished last time, and then we are going to start section 3. So in section 2 there are also a few things that will be needed in section 3. So let me briefly review one more time. We have done this many times, but anyway, so we were talking about searching algorithms which operate on some array of elements of some data type and uh, find an element in an array, or we were talking about test uniqueness, so whether two elements in an array are equal or not. Okay, and then uh, we discussed linear search, which works for arbitrary arrays and it has linear complexity. And then we said for ordered arrays we can do better. We have binary search, which is uh, logarithmic. Um, and then we were talking about various types of uniqueness and hashing as an improvement. Okay, so then these were our criteria according to which we were discussing various algorithms. So what does the algorithm do? Which operations do we use? What is the idea behind the algorithm, which I said is very important, and then the analysis of the complexity of correctness, and in certain cases, the proof that there is no faster algorithm, at least up to asymptotical constant. Okay, so and the last thing that I have done was the 1D and 2D range counting. So this was a little bit short. So I will say a few more words again. So okay, the linear search was pretty naive. So go the array from left to right and then test with a given element. We said that this has uh, linear cost. Then uh, neighbor search was find the index in an array which between whose element is a given element y. Okay, and this we said also this is this is linear, but if we impose an ordered array, then we can use binary search. The idea was to always test to compare with the middle element, and then we saw that we can make the time logarithm. And then we were talking about uniqueness algorithms. So if you're given an array, find whether there are two elements in the array which are equal. And the first naive algorithm, unique one, was quadratic. And then we said if you have an ordered array, then you do not need to test any pair of elements. You can just take two neighbored elements, and this will give you linear complexity. And then we said, okay, we wanted to have an algorithm which is faster than quadratic, but does not require the array to be sorted. Okay, this was the motivation behind what followed then. And the first idea was, let me write this one more time. So I call this database uniqueness. Okay. So a way of potentially testing faster uniqueness of whether all elements are equal, or some elements are equal or all that or are distinct. And the idea of this was to use the value of some of these elements as an index in an array, assuming that the values are non-negative integers. So you reserve an array here. Okay, so you reserve this array and you use this as a database for whether xn was encountered or not. Okay, and this is why you do this with Boolean, because Boolean is again, I mean, I said this, I must have said this, but Boolean is a data type which has only two values, true or false. Okay, and I mean, for everybody who knows C or so, we tacitly identify true with 1 and false with 0. Okay, so these array elements, they take only 2 values, and the value is 0 if xn was previously encountered, not previously encountered, and 1 if it was previously encountered. Okay, and then we said we can we can operate on this kind of array, and then you have only one loop here. Okay, so you reduce the algorithm to something linear. Okay, but the problem was first that there is a memory consumption which depends on this number of values m, and moreover you have this initialization phase, which also in practical situations has to be carried out by code. So this extra will give you extra complexity. So the runtime, therefore, instead of O of n, is actually O of m. Yeah, and this was the problem. So when m is very large, this initialization will cost a lot of extra time, and this is what we wanted to avoid. And this then led to the idea of hashing. Okay, so the idea of hashing was that instead of using xn as the index in an array, okay, you use, instead of this xn, you use a value p calculated from this n, which we call a hash function, and then you try to store this element xn in a smaller array where p is now the number of values which is taken by this hash function, and p is much smaller than this number m. Okay, and we said that we can organize this, but a few things that we have to do is we have to change now the array elements to integers, because we need to store the xn in the array. Okay, so this was one thing, and the other thing is that we needed to take care of collisions. Okay, so you can have now different xi's with the same value of the hash function. Okay, and now they cannot be stored one above the other, they have to be stored one after the other. So what happens in practice is that you use the hash function also as an entry point in this array where to store the elements. Okay, and then we discussed that there is this problem that sometimes you have collisions. So this value of the hash function is 0, but it has to be written going over these previous values of the hash function, which are 3. Okay, so you have this problem of collisions. And now what is the merit of this? Okay, the merit of this. First of all, you reduce your memory consumption from O of m to O of p. Okay, where p is much smaller than m. Okay, so you save memory. This is the main thing that you wanted by using caching. And now, what was the runtime? And we said, okay, the runtime is you have a linear loop here, so you have something like n times, and then you have this collision checking part. And then we said, so it depends on the choice of the hash function. If the choice is good, then you can almost, okay, this is almost constant in average. Okay, in average. So in the average complexity, if you choose the hash function well, it's almost linear. Okay, the worst case complexity is still quadratic. We explained this. If all the hash functions are equal, then you cannot do better than the unique one algorithm. But in average, the complexity is almost linear. Okay, so this was the advantage of the hashing. And then we discussed some things like order statistics. This is choose an element, choose an index in the array so that you have a given number of smaller elements or a given number of larger elements. This is what we discussed last time. So and then we said that for when the array is sorted, the answer to this can simply be given by the number k itself. When you have a sorted array, you must again be careful. I do not want to repeat this every time, but I said that there is a problem of uniqueness of the output. Okay, and in this case, the output is not unique, so these two algorithms, they can give you something different, and nevertheless, they are both correct when the array is ordered. So, okay. And then we discussed the issue of 1D range counting. Okay, so this is the number of elements of an array which lie between two given elements x and x prime. And the first was the naive algorithm. Okay, so simply go from left to right and test. And then we said that we can use our binary search capacity to improve this complexity from linear to log. Okay. So by using the capacity of the binary search, we can improve this O of n of the naive algorithm to logarithmic. And the last thing that I was discussing now, I was a little bit short on this, but I think this will be discussed later in the class. Okay, we will return to this data structure later, the data structure of the binary tree. I said that in some cases it is useful to store the elements x1 to xn not in an array, but in a structure which looks like this, which I call a binary tree. So you have a parent node which is at the top. If every node has has two outgoing nodes left and right until you land in a leaf which has valence 1, and in the leaves are stored the elements of the array in an ordered way. Okay. And then we said to make this more efficient, we store in every non-leaf node all the elements which are in the leaves below it. Okay. So, and then if we have this, then we can, there is a way to check whether the content of a node is in a given interval or not, or it is completely outside of a given interval. And so we do not need to go through all the elements of this node to test whether they are between x and x prime. Okay. And by using this, you can reduce the, so you can do this one range counting again in logarithmic time, because you need to do some logarithmic descent for testing where is the position of x in this array, and you have to do this one more time for x prime, and everything between x and x prime will be in the 1D range. And so what should be stored in these nodes here is actually not the elements themselves, but the number of elements, and largest and smallest element is enough. Okay. So, and if you do this, then you have another type of logarithmic algorithm for counting the range, which in this form it is more or less in some sense equivalent to the binary search. Okay, so the idea is very similar, that you have some kind of descent into smaller pieces, and at every time the position of your x in this array is located up to 1/2 to the n of the array size. Okay, so the idea of the descent in the binary tree and this of the logarithmic search is quite similar. Okay? And they also have basically the same complexity. But the good thing about these binary trees was that you can generalize this to two-dimensional. Okay, to counting elements in an array of pairs which are between a given pair and another pair, where this is called key components, but this means that x should be less than xm should be less than equal to x prime, and y should be less than ym, which should be less than equal to y prime. Okay, so if you draw this in a plane, it is like you count the points in a rectangle. Okay? Given by the left lower corner is xy and the right upper corner is x prime y prime. Okay, and for this sort of problem, you can modify the 1D search tree algorithm to a 2D search tree algorithm, where you do the following. So in the 1D algorithm, you had nodes in which you just store the elements which are below. Okay, now what you do is you do not store the elements themselves, but you store in every node a 1D search tree, okay, in which all these leaves are are featured, but the search trees itself is structured with regards to the Y component. Okay, so you have a binary tree whose non-leaf nodes are themselves binary trees. Okay, and I mean I did not make this until the last detail. So for example, you see at this point I didn't write the pseudocode. Okay, so it is a good idea for you to think about it, what this means and how to write the pseudocode yourself. Okay? But so the idea is that if you're given such pairs x comma y, x prime, y prime, you first locate all the nodes with respect to the interval x, x prime. Okay, in each node which is relevant, you apply this algorithm one more time. You descend in each node into the subnodes of this tree, which are given with respect to the division between 1 and y prime. So, and every such descent will cost you log n of operations, because the tree is assumed to be well structured, so the depth is logarithmic. And then, so for one D search, you need O of log of n operations, and for 2D search, you will need O of log squared of n, because every operation now becomes log of n operations with respect to the y component. Okay, so this is how you can search efficiently in binary trees. So of course there is, I mean, I said it last time, but let me say it again. So of course you need to have some procedures to maintain this data structure. So for example, how to insert elements, etc., how you generate these trees and so on. So this is not discussed at this point. We'll talk about these problems later. Okay? But in principle, if you have a well-organized binary tree, you can use this to efficiently search for elements in a rectangle or in an interval. Okay. So this was the end of section 2. Okay, so which is again summarized here. So this was okay what I was talking the last 3 lectures. So it is a good question. So I said if you do it this way, the memory consumption is m times log of n, because every element is stored once for each level of the tree. Okay, and then of course you have n elements where it stores log of n times, so you have n of log of n. And then I said, okay, in fact, I said this last time, but let me say it again. In fact, you do not need to store all the elements. What you need to store in each node is only the largest element, the smallest element, and the number of elements. So for this counting problem, for counting, you do not need all the elements. Okay. Okay, for counting, you do not need all the elements. If you want to, but however, if you want to output the set itself, okay, then you would need this list, or at least it is efficient to have the list, because you do not want to, if you do not have this list here, then you would have to go down and collect all the elements for all the nodes below. Okay. So for if you want to have the set, then it is better to store these elements. And now the question is why? Okay, what is O of log of n? I mean, you need to copy. Copying this list of elements is regarded as one primitive operation. Okay, even although the number of elements can be up to close to capital N. Okay, in this sense, the complexity of this algorithm is log of n for writing the whole set. Okay, for counting it is easier. If you just want to count, you do not need to write all the elements. You simply write the largest, the smallest, and the number of elements, and then you just add. Okay, so this is what uh, I, this is what this O of log of n means. So even if the output is close to capital N as a set, okay, you count copying the content of this node into the set as one operation. In this sense, you get log of n. For counting, it is easier. For counting, it is simply you add the number of elements, and then okay, it is one operation. So then there is no problem. And it is similar for y for y tree. Okay, because basically at every node you have to do one more time the procedure for the x tree, except that now instead of the x coordinate you put the y coordinate. And you must be careful, of course, if you have x and y's, then what stands in the leaves is again all the pairs of x comma y. Okay, so you do not write only the x coordinates in the one tree and the y coordinates in the other tree. You write all the x and y's. They are stored in all the leaves. Okay, so this is okay, where because you want to get the elements themselves. You want to count them. So you need to write both pairs, but you need to structure the tree on the first level with respect to the x coordinates. So instead of this one, now imagine that you have a pair 1 comma something, and then something doesn't matter here. Okay, and instead of this 6, you have a pair 6 comma something, and what is the other one doesn't matter for how the tree is organized. Okay? But then inside this node there is another tree where you have this 1 and 6 as well, but now the structuring is with regard to the other components. Okay? And now what was after the 1 and the 6 matters for structuring this tree, which is inside here. Okay. So I mean I cannot explain this in better detail. So let's try to think about it. Okay. Maybe we will talk about this problem later on again. So this is at least the idea. We haven't written a pseudocode about it, but this is at least the idea. So you have a tree of trees, and then you descend first with respect to the x coordinate, and then with respect to the y coordinate. And every time you descend, it will cost you a factor of log of n. Okay? So you need to descend twice. Now you have log squared of n. Similarly, you can generalize this idea to 3D, 4D, etc. For 3D, you will have O log cubed of n and so on. So you can count triples of integers in a product of 3 intervals, for example. Okay, this will be O log 3 of n. Okay, so now let me try to finish this here. So now okay, so we will talk now about the problem that I have discussed, I mean, briefly a couple of times in connection with searching this of sorting. Okay, so we will talk about various types of sorting algorithms. We will start with the most naive ones, which are the bubble sort, the selection sort, and the insertion sort. They are very, very similar in ideas and very similar in complexity. Okay, and then we will talk about merge sort and quicksort, which have a different strategy. They divide the array into pieces and then operate recursively on these pieces. And merge sort will have the better worst case complexity, okay? But it will have a higher memory consumption because it requires a certain copying procedure. And in quicksort, we try to remove this copying problem, but then the worst complexity becomes again not so good. And the reason of this is that when we divide the array, when we divide the array, there is a certain disbalancing problem, okay, that occurs, and this is what we will talk about in the linear time median. So how to fix this disbalancing problem, but this will become already pretty technical, so we will need some time to explain it. Okay, and sorting in linear time will be, again, we will try to explain some algorithms which have very good complexity but work under some special extra assumptions. Okay, and I do not want now to repeat very much about this, because this criteria that we had in about searching algorithms, essentially the same reasons or same considerations apply for sorting as well, and for other algorithms, in fact. Okay, so you always have these specifications according to which you estimate the merits of algorithms, their complexity, and how do you design them efficiently, and so on. So I don't want to repeat this. So these are kind of fundamental criteria of algorithm analysis, which always occur. So okay. So what is sorting supposed to do? Let's just say first something about the specification of sorting. So I have, say, an array of elements of some data type X, which has an ordering relation. And I remind you, okay, unfortunately, we weren't able to finish fixing this problem. Every time you encounter this box, remember that this is due to my PowerPoint's failure to display this special font. So every time you have this rectangular box, imagine that this means the set of natural numbers. Okay, so n is a natural number, and I have a sequence of elements in which usually is stored in some array. And what I want is, I want a permutation pi, so that the permuted elements are ordered. Okay, so this means x pi 1 is less than equal to x pi 2, and etc. And in many cases, so let me say this from the beginning, because you will see this. We will not talk too much about this permutation itself. Okay? So instead, we will simply try to output the ordered array. Okay? I mean, if you have the permutation, you know how to permute them, but in the end, you simply want to have the elements ordered in this way. Okay, and if you have two equal elements, then pi doesn't have to be unique, but in most cases it will be enough simply to output the array x pi 1 until x pi n, not pi 1 to pi n. Okay, so now what is a cost model? Okay, it will be similar to searching, except that now we have, and we are allowed to operate on the array itself. So the array is not read-only. Okay, I can change values of elements in the array. So for example, okay, and now I swap into elements in the array. I will count with cost 1, and the other things are the comparison, the arithmetic cost 1, similarly to the searching problematic. So I have now an extra type of operation, which is changing elements in the array, or assigning elements in the array to some value. Sometimes I do not only exchange them, sometimes assign them to some variable, etc. But all these assignments will have cost 1. Okay. So this is not okay. Okay, not very surprising to have this kind of counting rule. Okay, so okay, what can you do? What are naive ways of sorting? And the first idea, okay, and I already mentioned this before. So this is the idea of bubble sort. So what does bubble sort do? You will see the animation in a moment, but the idea of the bubble sort is that whenever you define a variable m, and you want to have x to the n first to be the largest element in the array, then you want x to the capital N minus 1 to be the second largest, and etc. And you accomplish this by setting m to value n minus 1, etc. So n down to 2 means n minus 1 until you get to 2. And you go through all the pairs of neighbors of the first m elements of this array, and you always you choose the right one to be always bigger than the previous one. Okay, so this means if you find that the left one is bigger than the right one, then you simply change them, and you go further. You step further with this case. Okay, and what happens after this iteration is, so after this loop here, this inner loop is finished, xm will be the largest of the elements x1 to xm. Okay, and and then when you can do this with this loop, then you can start, then you do this for m is equal to n. This means xn will be the largest element. Then you do this for n minus 1. This means xn minus 1 will be the largest from x1 to xn minus 1, etc. Okay? And the reason this is called bubble sort is kind of because you always, bubbles go up. Okay, bubbles go up, and you always want to your largest your element xk. Okay, you always want your element xk to go up. Okay, so the largest element goes up until it goes until x to the small n. And now I think here is an animation. So let us follow this animation and see what he does. What so these red boxes, okay, these red boxes are these two neighbored elements which are compared here. And after every comparison, the right element is on the big element is on the right. So 8 is bigger than 4. This means 8 moves to the right. And after you go from the 1 to the end, then you know that this element is the largest. So now you simply forget this element and do this only here. So you start first 2. 5 is bigger than 3, so you have to change. 5 is bigger than 1, so you have to change. 5 is not bigger than 6, so this means you just move to the right. 6 is not bigger than 7, so you just move to the right. You don't swap. 7 is bigger than 2, so you have to change. And 7 is bigger than 4, so you have to change again. And now what happens in the end is what stands here is again the largest among all these. Okay, and now you continue. So these are okay, and now you have 6 elements to sort. So and then now you repeat the procedure. So these are all increasing. Now 6 is bigger than 2, so you have to change. And 6 is bigger than 4, so you have to change. And 6 moves, 6 becomes the largest. Okay. So this is the idea of the bubble. So m is just the index of this rightmost black element, which the rightmost non-black element. Okay. And at the end of this loop, okay, xm is correct, and then you simply this element is now correct, and you can simply put m down, and you can continue doing it. And obviously, the last element where you need to swap something is when n is equal to 2 and k is equal to 1. So this is why you need to go down only until 2. So after you go down to 2, then it is done. So here now, there are 3 comparisons, and okay. So this is the idea of the bubble sort. Now, why is this correct? And I explained this, but it is written one more time here. So what this loop accomplishes is that that xm is the largest among the first m elements. Okay, and when m is iterated, this means that for a given value of m, and you finish the loop here, so at this place, okay, xm is less than xm m plus 1, etc. until xn, and the first m minus 1, they are in some way which you do not know. But if you go down with m is equal to 2, then these less than or equal relations are established all over here. So in the end, you have a sorted array. So it is not difficult to see that this is okay. This algorithm is correct. Now, what is the complexity? And so what do you have to do? You have a loop which goes from n to 2, and you have a loop which goes from 1 to n minus 1. So you have n plus n minus 1, so n minus 1 plus n minus 2 plus etc. Okay, and this is quadratic. Okay, so this is very easy to see that if you do this in this way, then the complexity of this is quadratic. So we will be able to do better later, but okay. So this is the first idea. So you can do like that. So this is the bubble. So now there is a similar algorithm which is called select sort. And again, there is an animation. So maybe let me put the animation here. It is a little bit faster. So unfortunately, it is so fast that I do not have the time to explain every step while the step is being performed. Okay, so this is closer to the speed of a computer than to my talking. But anyway, so what is the idea of the select sort? So m now is a number such that the first m minus 1 elements of the array are sorted in the beginning, and when you exit this loop, then also the first m are sorted. So this means that this loop will determine correctly the value of the mth element of the sorted array. And how does he do this? So what he does is he memorizes, or he maintains an extra variable min, which is the index of the smallest array element between xm and x capital N. Okay. So now how do you determine this? Well, okay, the first thing is you put it to m, and then you run a loop from m plus 1 to n, and every time you find a smaller element, you record its index in this variable min. So at the end of this loop, okay, at the end of this loop here, so here is the end of this loop. And the end of this loop, min will be the index of the smallest elements between xm to x capital N. And then what you do is you simply exchange xm with the smallest element. So this means that now the new value of xm is the smallest among xm to xn. And then you argument m by 1, and then you do this again. So now this is what is being done in this animation here. So the yellow elements, okay, the yellow elements here are x1 to xm minus 1. Okay, these are the already sorted elements. And what is in red, what you see in red is x min, and what you see in blue is xk. Okay, and now see, every time the blue goes over something which is smaller than x min, it changes the x min. Right? So for example, 85210, okay, 2 1. So every time it goes with this blue element down until the end, and every time it finds something smaller which is smaller than the red, it makes the red to this new element. Okay, and at the end, when after he ran down until the end, then he changes, makes this exchange. Okay, so now again, so why is this correct? Okay, it's not difficult to see that this is correct, because the first m minus 1 elements are increasingly ordered here in the beginning, and at the end, the first m elements are increasingly ordered, and the others, the rest is in some way. But when m goes to n, then this less than or equal relations continue here, and at the end, when m is at n minus 1, you will have this until here. Okay. So and then the array is ordered. So it's not difficult to see that this is an ordering algorithm. So now, what is the runtime? Okay, the runtime is quadratic again, because you have one loop here, okay, and you have another loop there, and so this means for m is equal to 1, you have n minus 1. For m is equal to 2, you have n minus 2. So n minus 1 plus n minus 2 plus etc. until 1. This is quadratic again. So the iterations of this inner loop will be quadratically made. So again, okay, this gives you a quadratic algorithm. And now there is a the third idea, which is this of insert sort. And what so what does this do? Okay, the idea of this insert sort is that you always look, you have a certain number of sorted elements, which are here in black, and then you always look at the first element which is not sorted, and then you try to insert this unsorted element between these other elements so that this whole array becomes sorted. So for example, 2 had to be inserted here. Now you take 4, which is the non-sorted element, and you have to insert it here. Okay. So this is what is that. So how is this being done? Small m is the index of the first non-sorted element. Obviously, one element is always sorted, so you can start with 2. Okay, and so I save this element in y. So what is the red box now is the value of this variable y. And then I go through the list of the previous sorted elements from right to left. Okay, you see that I'm decreasing in this loop. So I start with m minus 1 and go until 0. And go until, in fact, as long as the elements are bigger than y. Okay, so this means here I will have to go until this element, because this is bigger than y. And now this element is no longer bigger than y. And then what I do is I copy the elements to the right. So so every time this is bigger than this, I copy to the right. And then at the end, I insert the element y at the right place. So so this is what this does. So it is it takes the first non-sorted elements and tries to put it at the right place. This means that I always have to move certain piece of this array to the right. Okay, and I have to find out how many do I have to move to the right. And now, I mean, practical hint: when you move to the right, you always have to start from the right. This is why you have to take k to decrease, okay? Because when you move to the right, you always have to start with the rightmost element. If you start moving the left element to the right, then you simply copy the element all over the place. And this is why you have to, in this loop, you have to do this decreasing. You have to start from the highest element and then move up, move down. Okay. So this is what the insertion, the insert sort of. And again, so what is why is this correct? Again, it is like for the previous two. So in this place here, okay, before you start the iteration for m, the first m minus one elements are sorted. And again, when you are here at the end of this iteration for m, then the first m elements are sorted. So now this means after this iteration for m is done, you're in this situation here that the first m elements are sorted, and then you have some remaining other elements. But when you move m from 2 to n increasingly at the end, see, all the elements will be sorted. Okay. So okay, it's not difficult to see that this is correct. Now, what is the complexity of that? Again, it is maybe it is a little bit better, but it is not much better. So you have an outer loop, okay, here. So you have an outer loop here, which gives essentially a factor of n, and then you have this piece. And now you see, in general, when you take some element like so when you take this element 7, how many operations you have to do this shifting until you find the position of the 7. Okay, so and sometimes it is very much to the right, then this loop is very short. Okay, but if the element is small, okay, then you have to run through this loop you have to shift very many elements. So for example, 4, this means you have now to shift 4 elements until you can insert this here. Okay, so now in general, okay, in general, this can be small or this can be large, but in the worst case, you will always have to shift the entire array to the right. So this is kind of okay, so this is gonna cover less than n minus 1 or something like that. Okay, but if you have n times n minus 1, you in the worst case you always have quadratic. So if let's say if the element if the array is in exactly the reverse order, then you have the maximal number of these shifts. So when you have small elements, they will always have to be inserted very much to the left, and you have very many shifts like this. So here you will have to shift 5 elements in order to insert these 2. So you cannot avoid, in general, you can have fewer, but you cannot avoid having something which is proportional to, okay, maybe I should write this more precisely, let's say, you can have here, you can give here k. But if you have a very large loop of this inner, okay, very large number of iterations of this inner loop, you will still get something quadratic. So you have n times n plus 1 plus until 1. So this is still quadratic. So in the average case, it may be a little bit better. For example, for a sorted array, then it will simply be linear, okay, because this loop will be empty, okay. But for in the worst case, it will definitely be quadratic. And since we consider here mostly the worst case, you can basically say that the runtime of the insert sort is also quadratic. Okay, so this is maybe a little bit better than the previous two, but really not much better. So okay, and so you have these three ideas. And is it possible to do something to do better than quadratic? And it is possible, but you need a different idea. So iterating like from left to right doesn't help you all that much. So you need some other idea. And this idea is I mean, it goes under the principle of divide and conquer. Okay? This is a general paradigm of algorithm design, which you will encounter it at many places. The idea is to use the capacity of the algorithm itself on a certain piece of the array. Okay, and so if you implement it, it will be like you have a procedure calling itself recursively. Okay, so you will have something like that. So this is the idea behind both the merge sort and the quicksort. They are similar in some way, but okay, let's start with first with the merge sort. So what is how does the merge sort work? Okay, again, so these are here the natural numbers. Okay. So how does the merge sort work? And the idea of the merge sort is I will split my my array into two halves. Okay, so into two halves. Now, of course, the length of this array, which is capital N, doesn't need to be in an integer, so n half you have to round it up and down, but it should be approximately half of the size. Okay, and you copy the first half of the array x into the array y, and you copy the second half of the array x into the array z. Okay, so this is what this does. So the first one is just copying, and this is copying with an index shift of L because the first L elements of y landed into x. Okay, so I have now two arrays y and z of approximately the same size, which is half of the size of x, and y contains the first half of x and z contains the second half of x. And then I use the capacity of this merge sort recursively. So I assume now that I can merge sort these arrays y and z themselves, and regardless of what is done in this algorithm, at the end I'm certain that the array y is sorted and the array z is sorted. Okay, so now I have two pieces of the array x which are sorted. Okay? The first half of x is sorted and the second half of x is sorted. Now the problem is, of course, I do not know whether all the elements are in y are less than equal to all the elements in z. Okay. If all the elements in y are less than equal to all the elements in z, then it is very good because then I can simply join y and z and then I have a sorted array. And we'll return to this issue when we talk about the quicksort. But for now, when I copy the first half and I copy the second half, of course I cannot know that there is an element on the left which is bigger than some element on the right. It is very well possible. So I have two sorted arrays, but I cannot simply join them. I have to merge them. Okay, I have to combine them in a proper way so that I get the array X. And this is what is done here. So basically, what this this code does is it is written now taking L and R to be from the initial values, and then you always decrease them. So what this does is it takes it compares the rightmost elements of z and y and chooses the one which is bigger. Okay, so if ZR is smaller, then YL is bigger, and then the element YL is copied into X, and if ZR is bigger, then ZR is copied into X. Okay, and then you decrease the index of the piece where you copied something by 1. Okay, so this means you always copy elements from these two elements from the right to the left, okay? But you always choose the bigger among the two. Okay, and now in the animation that follows, the same thing is done, but it is done from left to right. So it is only a technical, I mean, a technical detail. The idea works from left to right as well. I mean, I can, if I have two sorted arrays, I can compare the elements of these two arrays from left to right and choose the smaller among of the two. Okay. So, and this is what is being done. And this, okay, so what does this do is here, what these loops do is, when you're through with the elements of one of the two arrays, then you simply copy the rest from the other. Okay, this is what this code does. So this code here is some kind of recombination, or okay, this is the actual merging. So this is the merge. This code is the actual merging. Okay, this is why this is called merge sort, because I split it into pieces, I sort them, and then I try to merge them properly. Now let's see, there is here this animation. Okay, so now here is my array, which is not sorted. I split it into two halves. I split the house into two halves or quarters, and then I split the two quarters, the four quarters, each one into halves of length 1. Okay, now sorting an array of length 1 is clear what has to be done. So what this does is here is the recombination. I always have to compare the rightmost elements and take the smaller of what remains. Okay, so 2 is now, this is a 4 here, which you don't see. So 2 is less than 4, so I put them in this order. Now I have this and that. I compare first with first. I take the smaller, then 5 with 3, and then I have to copy the remaining 2 elements here. So now 7 with 2, I have to take the 2. 7 with 4, I have to take the 4, and then these 2. So this the move of 7 and 8 is what is done here in this last. So 1 with 2, you take 1. 2 with 3, you take 2. 3 with 4, you take 3. 4 with 5, you take 4. 5 with 7, you take 5. 6 with 7, you take 6, and then 7 and 8 remain. Okay. And now at the end, the whole array is sorted. So this is the idea of the merge sort. So the idea of the merge sort, this follows this divide and conquer principle, is I use the capacity recursively by splitting the array into 2 halves. And then I do not know, unfortunately, whether everything on the left is less than equal to everything on the right, but then I have to do this recombination. Okay, so now it becomes a little bit more complicated to see what is the complexity. Okay, now we have to use master theorem or whatever. So let's say Tn is the complexity of the merge sort algorithm for an array of size capital N. And now what does this give you? Now you have to start getting a little bit more careful than before. So this here will give you O of n. Okay, so this is a copying procedure. This will give you O of n. And this here, so now you have to think about it. This also gives you O of n. And the idea is that, so R plus L are equal to n at the beginning. So when you are here, okay, when you are here in the beginning, R and L R plus L are equal to n. And regardless of what this test does, exactly one of the two decreases by 1. This means this loop will exit after all of n steps. Okay, and these two loops, they simply give they decrease the remaining L to 0. So all of this is O of n. So this recombination, so the copying, both the copying and this recombination part, they're both O of n. Okay, and this is what gives you here this O of n. So now let's see whether he used exactly the same rate. No, okay, so I can do even like that. So all of n comes from the copying and the recombination. And then you have two recursive calls, which are here. So now let's do a double line. And this is what brings you this factor. 2 times t of n over 2. Okay. So now you have an equation that you can put into the master theorem, and the master theorem tells you that this function is n times log of n. Okay. So the complexity of this algorithm now is n times log of n. Okay. So, but what is a little bit of a problem in this is that you have this extra copying this extra memory consumption. You see, every time when you run this, you always need these extra arrays y and z. Okay, and the size of this y and z is together is the size of x. Okay? So you for example, if you have an array of 8 elements, you copy them into 2 arrays of 4 elements, then you copy them into 4 arrays of 2 elements, and then you copy them into 8 arrays of 1 element. Okay, this means that the size always decreases by half, but every element is copied at least as many times as until the size decreases to 1. So every element is copied log n times, and if you have n elements, you have n times log of n memory consumption in this form. Okay, so you have this extra copying. Now there's I mean, I don't know. So I got this question once in the chat. Okay, so some students are smart and they notice certain things. Do you really need as much? And the answer is okay. So you see, when you copy y and you copy z, as long as merge sort y runs, you do not really need the memory for that. Okay, because y, the merge sort on y operates completely independently from z. Similarly, after the merge sort at y is finished, you do not really need any longer all the memory that this merge sort allocates in recursive calls. Okay, so all the memory that was allocated in merge sort of y can simply be released. And then you can see that actually you do not need, you can save memory. So as long as you do not allocate memory that you do not operate on, or you do not operate any longer on, you can save this. You can save some of the memory. Let's maybe go back here to the animation. To maybe I can explain this on the basis of the animation. So. So the idea is that you do not really need to maintain all this memory simultaneously during the entire running time of the algorithm. So you need y only here and you need z only here. And once this is finished, you can simply release it. So for example, now you see you divide it, okay, and as long as you operate here, what happens here is completely irrelevant. So, and this is why, for example, if you use a parallel computer and you want to run this and this simultaneously, then of course you would need both. But on a normal computer, when you run one after the other, as long as this run, you do not need Z, and as long as this run, you do not need Y anymore. So, and with this, you can reduce the memory consumption. And now I do not want to make every detail, but you can think about it. So if you're allowed to release memory and reuse it for some other purpose, then how much memory would you need? I think you can improve this, but I don't want to say the details. So please think about it yourself. If you are allowed to release memory for finished or not yet done recursive calls, then you can improve the memory consumption. Okay. So this is this is something that you can do, but unfortunately there is no way to avoid this copying. Even if you use the same memory multiple times, okay, even if you save some memory by not doing it this way, you still need this copying procedure. There is no way to efficiently recombine pieces of the array without using an extra external array. Not efficiently. Okay, you can do this, but it will be not more efficient than a bubble sort. So you always in this merge sort, the merge sort is very efficient, but it always has the problem that you need to copy some pieces of the array. So you always have extra memory. And now my time is nearly over, so I do not want to make too much. But next time I will start discussing the quicksort. Okay, and the idea of this of the quicksort is you want to improve the merge sort so that you do not need this extra copying this extra memory copying process. So you want to operate on the array X itself without allocating extra memory. And you will see that you can do this, but there is kind of a there is some kind of a problem. Okay? That this is the problem of this balancing the division between these arrays Y and Z. So what will happen is that you cannot easily ascertain that Y and Z have approximately equal length. This is what you will have. So you can save this extra array copying procedure, but you will have first the problem that Y and Z, one can be very large and the other can be very small. And then we'll have to discuss how to fix that problem, but this is already, this is now a longer technical discussion, which will occupy a lot of the material in section 3, and so this is things for next week and maybe next week. Okay, so we will discuss this. We will discuss this quicksort and the linear time median problem in later lectures. So okay, now I think that my time is over, so I do not want to do more today. Next time I will start again by doing a review of what I said today. So these naive quadratic time algorithms, and then I will say one more time what is being done in the merge sort, and then use this to motivate what the quicksort algorithm, and then to discuss the related problems that occur in the quicksort algorithm. Okay, so I think that now I should finish. Thank you, and see you next week.